based in our Munich office. I spent the last 15 years with McKinsey in Europe and the US, but also in Asia. And my work focuses on the powertrain transition up and down the value chain.
Hi everyone, I'm Paolo Oliveros, based out in the Detroit office, 3 years with McKinsey, focused on electrification topics and powertrain optimization.
And hi, I'm Dustin. I am a research science specialist out of Boston, and I work a lot with our electric vehicle forecasting and tracking US regulation, including the IRA, EPA regulation, and most recently the ongoing tariff discussions. Great, so I can kick us off. So I think it's no secret that there have been a few challenges over the past months and years of electric vehicles and profitability. And as we can see, this cuts across the entire industry with a lot of these headlines that we've highlighted of automakers who are either pushing back their electric vehicle targets or warning about profitability challenges that they're having already in the electrification space. This is quite broad across the entire industry, regardless of geography, whether you're a premium automaker, a volume automaker, or anything else. Next page, please. And really, this has not been helped in the past couple of weeks and months with a lot of uncertainty in the geopolitics space. So this is, as of earlier this morning, we have a view of what are the tariffs and policy changes that have been proposed in the United States. There have been other changes that we've seen in Europe, such as a slight relaxing of emission standards and increasing tariffs on Chinese automotive imports. But for right now, we're going to focus on the United States. Some of the more eagle-eyed among you may have already noticed that we're actually already out of date with the slide that we finalized about 2 hours ago, as more retaliatory tariffs have been announced from Canada after the steel and aluminum tariffs were increased last night. And so I think the story that we really have here is that there's a huge amount of tariffs and geopolitics that are making it a lot more difficult to plan around for the automotive industry. And a lot of these have been a very iterative process. So if we look at the Canada and Mexico tariffs, we saw a very iterative process where these tariffs were delayed. And then after they were actually implemented, we saw a process to remove the tariffs on automobiles and then on the USMCA compliant vehicles that we have, as well as various retaliations both by Canada and from Mexico that have been shifted a bit over time. And really all of this has been increasing the cost of a lot of components that we see in the United States, with the exact impact still being a bit up in the air as these change around over time. Beyond tariffs, we've also seen some changes coming for other automotive policy in the US, most notably with the carrots and sticks that we have of a push to remove some of the regulation, so specifically trying to remove CARB mandates via the Congressional Review Act, which is being submitted to Congress. And there's been the process that has been begun to revise CAFE standards for emissions for light vehicles at a federal level. Under the previous Trump administration, it took about 3 years, and so it remains unclear exactly how long this process will take this time around. On the industrial policy, we know that the IRA and the BIL are both policies which include a lot of industrial policy to boost electric vehicle manufacturing in the US. We know that these have been discussed in budget negotiations. We don't yet know exactly what these shifts will potentially look like as Congress renegotiates exactly what they're planning to do with these. Next page, please. And so for measuring the actual impact we have on here, we have two examples for the Tesla Model Y and for the Hyundai Ioniq of what the potential cost impacts could be. So we're showing a sensitivity test of both a less disruptive and a more disruptive scenario. So if we take a look at the Tesla Model Y on the bottom left, we can see that about half the cost roughly is going to be coming from our outside-in estimate from the actual cost of the components in this vehicle. And so that gets us up to the actual MSRP that we have on there. Of that content, about 70% of it is coming from the US and Canada, with another 20% of that content coming from Mexico, and about 10% coming from other places which are not disclosed. Once you add in the subsidy of that $7,500, that gets you to the lower cost that you're actually going to be paying today. And then as we add in a 10% tariff on that foreign content for Mexico and for the rest of the world, and as we potentially remove that $7,500 subsidy, that's already increasing the cost of that vehicle by about 23%. If you increase that tariff to 25%, and you remove the subsidy as well as getting rid of the battery manufacturing subsidy of 45X, that can potentially get you up to about a 35% cost increase. This looks different from Hyundai, which is going to be a lot more exposed for right now for their imported vehicles. Although the Hyundai vehicles that will be produced in Georgia will be seeing a much lower tariff that they would be exposed to in this case. And revenue subsidies would have a pretty significant increase on their cost of vehicles, although they would not be exposed to the battery manufacturing credits with their Korea manufactured vehicles right now. And again, all of this is to say that all of the policy changes which are being discussed in the United States have the potential to significantly increase the cost of electric vehicles in the United States. If we go on to the next page, we also can see what does this look like for the broader automotive industry. So we're showing on here top 10 vehicles produced sold in the US, and as we can see, of those top 10, 3 of them are being manufactured in Canada, so that final vehicle will potentially be exposed to tariffs. And then we see another majority of them are going to be actually manufactured in the US. But all of these vehicles, all of them have at least 30% of their content is coming from outside of the United States. So effectively, every single vehicle is going to be exposed to tariffs to some degree or another. When we look at that breakdown, we actually don't even know how much of that content is coming from Canada because these markets have been so integrated for so long that public data is not even tracked. So we don't actually know the exact impact of tariffs on Canada on a model-by-model level for these individual OEMs. We have received a bit more clarity from Canada and Mexico tariffs. We know now a lot more clearly that they're going to be applied to the value add of the content. So the scenario where we would have had every border crossing having an additional tariff, that's not taking place now. So the tariffs are a lot lower than what we potentially could have seen. But again, there's a huge amount of tariffs that we see that could potentially be increasing the cost of vehicles, and it's going to affect really the entire industry. As we see later in the month, as more tariffs kick in, so retaliatory tariffs and the tariffs on all automotive imports, we could see the cost of vehicles going up even further. And with that, that really just makes profitability and trying to find profitability in the automotive industry a lot more challenging. So if we move on to the next slide, we'll begin looking at how can OEMs actually respond to this uncertainty. And with that, I'll hand it over.
Yeah, thank you, Destin. And I think the viability of the business case of electric vehicles is a big question. Currently, we have only 3 global players that are actually profitable on their electric vehicles, and that's Tesla, still, that's BYD, and that's Li Auto. All the other players are not profitable on their electric vehicle, and we know for some players that are disclosing that no financials on profitability, they are still making a lot of losses. So many of these reasons why they are not profitable is, of course, limited scale, economies of scale in this phase of the adoption versus the high cost of investments and capex that goes into that. But it's also the higher bill of material and total cost of the vehicle, which they cannot pass entirely to the customers. So when we look at disruptors and Chinese players that are profitable already, we can actually learn a lot from them. And what we want to show here today is how we think about the business case of electric vehicles and how we think our pathway to profitability will look like. If we go to the next page, we see our framework. It's around, when we typically assess where do you stand on your EV profitability journey or on your business path to break even. And by the way, this holds true for OEMs, the same holds true for suppliers in the electric powertrain. Where do you stand on that journey? And we go a little bit along these lines on components and systems, design excellence. To what extent have you adopted actually new ways of design to value for electric powertrains? Often we see that many of the cost improvements or cost differences that we see between incumbents and disruptors or Chinese new players is because they are radically rethinking their requirements. Requirements that are, there's a lot of cost hidden. We talk about NVH, when we talk about durability, when we talk about the magnet degradation, etc. All these kind of little requirements. We see that some of the disruptors are actually rethinking those ones, and it changes also the cost. Vertical integration, here the second point, the first one is also a big one that actually it takes a lot of cost out. In some of the, let's say, classic incumbents world, we see often a really long supply chain behind individual components like electric drives, like power electronics, etc., where we have a tier X chain of suppliers. I've seen OEMs where they actually outsource their electric drive systems, and basically the tier 1 supplier has a total of 300 suppliers again to develop this electric drive system. So here, a very efficient value chain, and which also means that you have a more of system knowledge on the OEM side and maybe build to print some of the components that can also take out the cost of the electric vehicle. So that's lever number one. R&D approach and strategy. What we've seen also is that different regions in the world have maybe different customer requirements. They are also on different trajectories towards electrification. If you take China, 1 out of 2 cars today being sold is electric. Europe is not there, it's maybe 16%, 17%, and the US is still lower. And the customer requirements are also different. They require smartification and infotainment in China, less of powertrain, NVH, high speed, performance, etc. So here really a customer regional operating model, customer oriented, really what's really creating customer value is important. That's one thing, but also simplified configuration to satisfy customers can cost the cost of complexity, and also the R&D associated to that is significant. We also talk about R&D approach and strategy when we talk about time to market. We see that some of these disruptors actually bring cars to the market in solely 2 years, in 24 months, whereas incumbents often 48 months or even more for the development cycle of a new car. Of course, the faster you do it, the lower the cost associated to that, and that also takes, we can assess that. Manufacturing excellence, there's a lot we can do about CapEx efficiency. CapEx efficiency for, let's say, hybrid platforms, CapEx efficiency for pure platforms. Also new ways, new approaches, like unboxed manufacturing, which we talk in a second about, is taking also a significant cost out. On the sales side, we see that many of those disruptors have a direct-to-consumer business model and don't rely on extensive sales and distribution networks, which also adds typically 10-15% to the cost of the to the total price of the vehicle. So that can also make your total cost a little bit linear. And last but not least, something that's definitely not exploited today to the full extent, but I think going forward has a huge potential to improve the business case of the electric vehicles, lifetime monetization. If you can monetize in certain features that are maybe pre-installed, but then you have to pay for it on an annual basis, that can also improve the business case. So typically what we do is we assess where do you stand on your profitability journey, what are best practice levers that we can get. We tear down electric vehicles from China. We recently turned down the Cybertruck. What are the learnings that we can say? Because often we see really very insightful learnings, how they combine functionalities, how they integrate functions to really get the cost down of this system and focus what's really purely customer value adding. So I'd like to highlight, unless there are some questions right now, which I'm happy to take on the go, I'd like to highlight a couple of examples, focusing maybe more on some R&D innovations that we see in the market, and then also manufacturing. All right. Let's move to the next slide. So we've seen that there's a lot of innovation happening on the battery pack side that has also continuously enabled the car to be more structural, to be more cost effective. And what we've seen, originally we had cell to module to pack, then we had cell to pack, and what is now happening is actually structural battery pack, which is cell to chassis, in which basically the upper body of the chassis is part of the battery housing, and basically the seats are directly mounted on the battery housing. This actually saves weight, it saves cost, and yeah, we've seen many times that the battery pack is not fully replaceable with the car, but with the BMS, battery management system, being in a penthouse, we see that most of the actually service elements for battery actually are related to the electronics. So you have a serviceable BMS in the penthouse, and you can still service individual modules or cells in this pack, and or do that even electronically. So that's one way that we see adopting by many players these days, a cell-to-pack architecture for pure native battery platforms, and that can significantly take out a couple of $100s compared to a classical cell-to-module-to-pack structure. So if the economies of scale are look promising, I think this is a valid approach that we see adopting in the industry even more going forward. The next example that we want to show is here related to that. What are the benefits, right? I talked about you reduce the weight, you have less manufacturing complexity, and you have also basically more structural, some structural benefits. And we see here on the couple of right, those OEMs that are actually shifting to a structural battery pack. Tesla up and foremost, then BMW with the new class. They are also announcing that the Xiaopeng G6 has a structural back. BYD is standard, and Geely announced it as well. So many players are adopting this new way of battery pack configuration. Go to the next slide. We've seen that, we saw also here that, for example, it's just the long range, how much actually weight you save. It's around 20-30 weight that you can save, and we're talking about, also at least several tens of dollars that you can save. I've seen even $100 in some other vehicles that can be saved on that one. Of course, it's all related to the development effort that you need to put in it, the tooling effort that you need to put in it. You need to have a significant longer, higher volumes for that to pay off. Very good. If we go to the next chart, I would like to hand over here to Pablo. We'll talk about some integration functionality on the thermal management side, also which are innovative, which make the powertrain more efficient, and which can also help to save cost.
Yeah. Thank you very much, Patrick, for the introduction. So basically, we are discussing here potential opportunities to improve the profitability of EVs, and this is another initiative that we are seeing spreading across the industry pretty quickly. As Patrick mentioned before, we recently turned down the Cybertruck, but this is not something new to Tesla, how to integrate in the EMS system. Basically, when we moved from ICE to EVs, what we saw is a completely different structure of where the heat is generated. When we had the ICEs, basically the efficiency was around 60% in a good case, and you had a lot of losses in the engine. But now the powertrain components are really efficient, right? We have electric motors that can go up to 97-98% efficiency. We see power electronics with silicon carbide, and we will soon probably see some gallium nitride as well in the low power electronics. But basically very high efficient components that at the end generate lower losses. Now you need to be very smart of how you leverage the heat generated in those sources and put that heat wherever is needed in the vehicle. That is achieved through integration, and that is what Tesla has mastered. Basically what we see on the right is the battery may act as a source of heat when you're charging it, for example, at 250 kilowatt of power in fast charging. But you also might need to heat it up when you're in cold temperatures to make sure that it's charging at 20 Celsius, right, which is the optimal charging temperature. Cabin HVAC, we see the same approach than before, where you may need heat or cold in the cabin. And then the powertrain, basically, as I said, there are several components, the OBC, DC converter, inverter, the motor, CC bus, a lot of components that are generating heat, but less heat than what we saw before in the engine. Now, we move to the next page. What we're going to see is a comparison of what a very integrated system looks like and what a non-very integrated system looks like. The Mercedes QS, by the way, is one of the first generations. Model S and Model Y follow a very similar approach. One thing to consider is the Model S might be more expensive, or the shoot cost grows a little bit more because it's not being normalized by power. Model S is significantly more the rated power is significantly higher than Model Y. That's why you might see a higher cost, but basically the approach is the same. What you see is that the cost of the system is slightly higher because now you need to invest into a valve that integrates all the circuits in one. This has also been seen in the latest approach of Avatar, which also leverages a Nona valve for their system. But this was all started by the Tesla, which combines all the water cycle circuits, the one that circulates through the power electronics, the battery, the motor, the cabin, in the same structure. One thing that is particular about Tesla is they are able to achieve, the cost of the system is quite high, but it could be even higher. One thing that we see is that Tesla doesn't follow a typical approach of having a high pressure and low pressure filling valves. It's a completely sealed system, which you can reduce the cost of the valves by doing that approach. But if you have a leak, then you have to remove or replace the whole system, which is very risky. This is kind of the trade-offs that OEMs do. We see, for example, BMW still using pressure valves, but Tesla don't using them. So it's just a trade-off of your risk and reward. If we go to the next page, what we see is what is the effect of having a fully integrated system. If you have a fully integrated system, now you don't need to create that heat. So if you need, for example, to heat up the battery to the 20 Celsius aforementioned, you don't need a PTC heater in the water glycol loop for the battery. Or if you need to heat up the cabin, you now don't need to have the PTC in the cabin loop. You might opt to do it because the PTC heater, what will allow you to do is heat up the cabin faster. But if you're not concerned about how fast you can cool the cabin or the battery, you can run the motor, for example, in a low efficiency point. So you create a lot of heat that gets transferred to the water glycol loop, and you leverage it to heat whatever part of the vehicle you need, the cabin, the battery, or whatever you need to heat up in that specific point. The effect is seen in the graphs, which is you're paying more in TMS cost because now you're integrating, and we are only talking about the bill of materials cost, right? Because we need to also discuss about how much cost you would need in engineering over the development time of a platform. You now need to have all the systems working together and a common structure that has to be integrated across very different teams, right? But the effect down the road is if you now are able to create that heat within the vehicle and not having a PTC heater that is taking energy from the battery to create additional heat that is not needed, what you can do is you can do two things. Or you downsize the battery because you don't need that portion of the battery to heat up the PTC heaters. Or what you can do is you increase the range of the car, right? You can follow the two approaches. The one we showed on the page is the one that reduces the cost of the vehicle, just to show it in a cost dimension, but you can also increase the range, which is also appreciated, especially by those high-end or premium segment users. There is also additional advantages in terms of less copper needed across the powertrain because of the lower heat generated now. But overall, the main driver is you're able to have a more efficient overall system. And this more efficient overall system, what it's going to allow you is to reduce the battery size. As we see in the page, regardless of how much you pay in extra cost for PMS, 10, 11%, whatever, the massive reduction you get in battery means that overall you're able to achieve 8-10% of lower system cost. So this is a way to improve profitability in a way that it's very smart. Tesla already doing it. We see Chinese OEMs that said Avatar 11 already using this concept as well. And then it's likely that we will see the same heat pump and optovalve non-valve approach in many OEMs in the future.
Cool.
With that, I hand over to Malu. Yep, go ahead, Malu.
Thank you. As a recap, what Patrick shared with us was like the 5 strategies to improve profitability. Most of what was shared, almost all of what was shared up until now is how can we improve profitability through design excellence, and basically we showed some examples. We'll switch gears a little bit and then talk about 2 other strategies. One is how a company like BYD was able to reduce its cost through vertical integration. Again, this is not an easy strategy to implement. It takes decades, years to get this right, and it requires like a full alignment from supply chain, from procurement, from R&D to implement such a strategy. But if done correctly, if done intentionally, this can certainly help reduce overarching cost. So what we see here on this page is the level of vertical integration that BYD has. across its different subsystems. It's a non-exhaustive list, but so we won't go through like all of the subsystems. Let's just look at three, right? Like let's look at battery. As far as battery is concerned, BYD is fully vertically integrated. What do we mean by that? It means like they control upstream, midstream, and downstream of manufacturing the battery. Right from mining the raw materials. For example, BYD has access to around to 6 lithium mines, at least one nickel mine that we know of, to like mine these rare mine these materials. And then if you move to the midstream, where they take these raw materials and manufacture cells, they have control over those productions too. As of mid last year, what we learned was around like 480 gigawatt hours of capacity they have across 26 plants for their LFP batteries, and another 45 gigawatt hours across 5 plants for their NMC cells. So yeah, they control the midstream, and then as we know, they also control the downstream, where like they take their cells, the blade cells or whatever the case may be, and then make the packs. So our estimates range around like 15 to 20% of cost savings that BYD can achieve purely through vertical integration, because now they don't have to pay. Not only is it faster to procure this end to end or even develop end to end, but also like the margins that they might have to pay to like the players down the value chain and up the value chain is not in question with this strategy. Again, it's not something easy for most players to adopt, but BYD has been intentional about it, and as a result, they're able to see they're able to see the benefits in their profit margins. Then, if you look at the vertical integration of its e-powertrain, it is vertically integrated end to end. So their e-motors, inverters, transmission, everything, all of these components they make on their own. Additionally, because they make it on their own, they also have the ability to make these 8-in-1 systems where they're just like packing their e-drive system with additional componentry like the OBC, DC-DC, VD, whatever the case may be, and make it super dense, super compact for packaging into the final vehicle. Another example that we can share here is EE systems. Again, they are not fully integrated here, but they're certainly giving indications that they intend to be more and more integrated over time. For example, in 2023, they entered into a partnership with NVIDIA for their ADAS SoC, and they have also set up their autonomous division with around 5,000 software engineers, giving us a sense that okay, this is something that they truly want to focus on and invest in. And if you've been following the news, recently they announced their God's Eye ADAS system as an answer to the FSD that Tesla has to provide. Again, what we're learning is while it has BYD's footprints all over it, it is not an initiative that it did on its own. It has had partnerships. It's leveraged its partnerships with NVIDIA and Horizon Robotics. So the long and short of it is not an easy strategy, vertical integration, but if implemented intentionally with a long-term view in mind, then it can certainly reap benefits. Move on to the next page. So that was the second strategy. The third strategy is an intentional investing around features that customers value. Bring another BYD example here. What we have noticed is that most Chinese companies, not just BYD, over-invest in features that the end customer can touch, feel, and interact with. For example, if you look at the BYD Seal, it indexes on providing better customer experience. It has not only heated but ventilated seats. It has this 15.6-inch rotating screen, which is interesting to interact with. It has wireless charging panels. a heads-up, a unit display, a driver monitoring system, so on and so forth. So it's like packed with features that the customer will interact with on a day-to-day basis. So on average, if we see the cost compared to like a Western OEM's interior features is certainly more. Then the question becomes, if it is more, how are they managing their costs? The answer is like things that the consumer doesn't see. They have engineered it in a way so to not only maintain performance at the level they wanted to, but also reduce costs. So the examples again are like BYD has the structural battery pack, much like what Tesla has. Secondly, it uses LFP instead of NMC, so another way for it to like reduce costs. And then if you look at the eDrive, it has a heavily integrated system, as I shared earlier. So it's not just vertical integration, but it's also system integrated, given it has a bunch of componentry within the eDrive. So it helps optimize costs in housing and high voltage harness componentry. What we are also noticing is BYD likely has its eDrives with higher torque densities at lower costs. And then if you look at its electronic and electrical system, another way in which they reduce cost is by applying zonal architecture. And as a result of that, you can, if well implemented, you can like reduce your harness costs meaningfully. So in essence, concluding, there are even in times of uncertainty, players in the automotive industry can implement multiple strategies thoughtfully, intentionally, to maintain or like improve the profitability margins. Any questions from the audience here?
Sure. Yeah, thanks for the question. Basically, what we're seeing is, and probably this question goes to the Cybertruck teardown or other Tesla vehicles that we see combining induction motors with PMSMs, but we've also seen recent announcements of externally excited synchronous machines as a very nice and promising alternative to permanent magnet synchronous motors. One thing that I can say about this is the induction motor has a different area in the torque speed curve where it's more efficient, and then the PMSM would have a different region in the torque speed region where it's more efficient. So basically, when you're able to combine two different regions where the two different motors are more efficient, then you can calibrate your system to make sure that at given torque speed, you leverage more one topology or the other. With this combination, for example, in the Model Y, we saw a significant increase in efficiency, just because, as I pointed out, you can leverage the characteristics of these two motor topologies to, at the end, increase the overall efficiency of your system. So it's a good question because this is another lever you can pull to increase efficiency. We discussed before the integration of the TMS. If you add up the other measure, which is motor topologies, you can have 2x increase in efficiency and at the end, reduction in battery size.
Cool. Then we have a question from Hartmut. Do you think switch to 800 volts as a standard will decrease system cost? The answer is a little more nuanced. There are some components where you will see reduction in cost. For example, we expect the high voltage harnesses to go down in cost because now you're increasing the voltage. But at the same time, to get to 800 volts, you will also have to invest in some other componentry like your power modules. You might want to change to silicon carbide. In this moment, silicon carbide is more expensive, but over time it could potentially go down. So you might have to like invest in componentry like silicon carbide, or for example, if you additional componentry required for like electrical isolation for 800 voltage might be needed. But if we basically take two battery packs, same capacity, double the voltage, There will be some systems like high voltage harnesses where you'll definitely see reduction in cost, and there might be like components like power modules where you might see short-term increase in cost. What other questions do we have?
We'll take that one.
Okay, go for it.
Yeah, so thank you, Ravindra, for the question. What we're seeing basically is it's a super good question. Basically, if you're now integrating all the cells under one structure, which is you don't have separate modules to have, different set of cells isolated. You have everything in the same structure. One thing that you need now is to be very cautious of which material you use to separate the cells. For example, the Tesla Model Y, which has a cell-to-structure approach, if they use a foam to make sure that the cells are isolated one with respect to the other. Now, if you have a thermal runaway in one of the cells, you won't have a spread across the rest of the cells, and it will just get isolated in that single cell to prevent that very dangerous hazard. So it at the end comes down to very cautious selection of which materials you use, and to make sure that you run the testing and validation to make sure that is indeed very effective under all the temperature circumstances that the vehicle may find.
Thank you. Pablo, there's another question. Do you think historic manufacturers will move towards cell-to-body to be profitable? We can't speak to what the historic manufacturers will do, but the question is cell-to-body battery pack more cost efficient than, say, cell-to-module? If done well, yes, because now the additional cost that one would invest in, like the module housing and then additional componentry is gone, so it can be basically it would be like a simpler battery pack, and as a result, it could help towards towards the journey to profitability. There's another question from Edward. Any downsides to BYD's integration, like lock into old technology? There are pros and cons to like putting everything in an 8-in-1 system versus having it be more modular. Pablo, what do you think?
I don't have a clear picture on the River Rock thing, but the downside I would see in integration, for example, and I'm going to talk about one precise example on BYD, is with regards to the power modules. They have started doing that, right? But they don't have the learning curve that, for example, a BorgWarner has, right? So when you take a look into the integration that they've done in manufacturing and design and everything, yes, you can leverage the cost reduction of doing this in-house, potentially, but the quality of the system, it takes years and years and a lot of expertise to develop this in a high-end manner. And, you can see the downsides of not providing the best value in your vehicles for a few years until you catch up in the technology.
What level of scale is typically needed to become profitable? EVs per year. What we have noticed is that of the OEMs that are profitable, we've seen around, Pablo, keep me honest here, was it like around 70,000 units per year? Like
60 to 80. 60 to 80, yeah.
60 to 80,000 units
That's
per year to keep it profitable.
Yeah. It's one lever, not the whole story scale.
Yeah, that's a good point. It is one lever,
Yes.
not the whole story. Just because you're making more doesn't mean you will be profitable.
Question from Dave. What impact have you seen, if any, from different electrified variants like PHEVs or extended range EVs? Mario has done a lot of work on extended range, but basically what I can say is you can leverage the same platform to develop different powertrains. By that, what I mean is you develop one vehicle, like for example, we could say the F-150, and you develop a BEV version, a hybrid version, and an ICE version. The implication is you now create more complexity in your base because your manufacturing now will have more inventory. you now need to have more design teams working for the same platform. But what then you make sure is that you capture more demand. So there are more customers that go to the market for PHEVs, some of them go for fully electric, and there are some that will not in the short term transfer to the electric world. So this means that you cover more of the demand. But of course, this has implications in your procurement is more complex, your design is more complex, and then your manufacturing, inventory, MPNL, etc. gets more complicated.
We still have quite a few questions coming in. We realize we are at time.